In this video, we're going to learn about chemical bonding. Two main categories of chemical bonding are covalent and ionic. And in covalent bonds, think co-sharing, together, cooperative. Electrons are shared. In the case of ionic bonding, electrons are transferred directly from one atom to another. And to tell whether a covalent or an ionic bond is formed, typically it's good to check the electronegativities of the elements involved. So in the case of, say, sodium and nitrogen, if nitrogen has an electronegativity of 3.0 and sodium of 0.9, the difference between those is 2.1. And this means that the nitrogen is really able to pull on the electrons involved in the bond to the point that it will full on rip away the electron from the sodium. That difference of 2.1 is rather large. A typical cutoff is an electronegativity difference of greater than 1.7. This isn't perfect, but it works pretty well for ionic bonding. In the case of covalent bonding, something like an oxygen bonded to a fluorine, that's going to be a 3.5 to a 4.0, and this difference of 0.5 is not a whole lot, so this is going to be a covalent bond. In general, a metal with a nonmetal, you're going to get an ionic bond, even if the electronegativity difference isn't necessarily exactly at that 1.7 or greater. This really is due to the fact that the metal has a low ionization energy, the nonmetal has a high electronegativity and high electron affinity, and so you do get this full-on transfer where the metal loses the electron and the nonmetal gains. Covalent bonds are formed among nonmetals that are of similar electronegativities always, or even nonmetals and metalloids, because metalloids tend to have not particularly low electronegativities, and so they can kind of pull back a bit. There's another concept called the polar covalent bond, and just for clarity, that means that although the sharing is not exactly equal. So an example of a polar covalent bond would be actually, say, the example from before where there's oxygen to fluorine. There's a bit of polarity there because that electronegativity difference of 3.5 versus 4.0 is 0.5. That electronegativity difference is noticeable. The fluorine is pulling, and there's a partial negative charge on the fluorine as opposed to the oxygen. A little bit more polar than this would be if we had, say, a fluorine with a nitrogen, where the electronegativity difference is between 3.0 and 4.0 is equal to 1.0. So this would be more polar. The nitrogen would be more partially positive than the oxygen in an OF, and then fluorine would be more partially negative than it was in the case of OF as well. In the case of a completely nonpolar covalent bond, that's when there's an electronegativity difference of 0. But I'll even go so far as to say that a carbon to hydrogen bond will be full-on nonpolar, even though the electronegativity difference is 2.5 versus 2.1 is only 0.4. That's something, but it's not enough to really get noticeable polarity. And finally, with our ionic bond, note that we have the full-on transfer. It's not a partial negative. That's what this delta means, partial positive and negative. It's a full-on negative and a full-on positive. Note that the positive ion has become smaller because it's lost in its valence shell, and the anion has become larger due to extra electron pair repulsion. So that's all for this video. Hope it's helped. Feel free to leave any questions or comments in the comment section below. And thanks for watching.